In this video, we're going to look at descriptive statistics. So what I have in front of us is the passenger list, or a subset of the passenger list from the Titanic, with some fields that we've added in previous videos. You can look at those. We won't be working with any of those. We'll actually be working with the fare in British pounds for this video. So let's set some space up here. We'll work in here. So we're simply going to start with the data tab and go over to the data analysis, which is installed via the data analysis Toolpak. So if you haven't done that yet, you can watch the video on how to do that. We're going to select Descriptive Statistics, which is right here. Of course, you can scroll down and select a lot of different things, but here you go, Descriptive Statistics, and it gives us a box to work with. So what I'm going to do here is I'm going to select the entire column, and the column I want is J. And my output range, I'm going to put it at, let's put it at L4. And I want summary statistics right here, so I'm going to ensure that's checked. Now I can play around with some of these things, but we won't be doing that in this video. So when I say OK, click OK, and I can expand this column here. We see that I've got all kinds of descriptive statistics. So we're going to go through these kind of in sets, and the first set that I want to talk about are these measures of variability. So the ones down here, well, really those. So let's just highlight those in some simple color here. You can see what we're talking about. Obviously, count is count. We've done that before, and you can use the count function to do that. Range, minimum, maximum, sum, those are pretty easy to visualize, right? The minimum is, well, the minimum, and we can calculate that, right? Equals min for that value. And again, I could go over here like I've done in previous videos and select that entire column, but we're going to be doing this a lot in this video. So I'm simply going to type it in. This is the range that I want. And there we go. There's the minimum. Interesting that someone paid $0. Or I'm sorry, this is a good mistake on my part, I guess, to point something out. I'm used to working with dollars, so here I'm thinking they paid $0. They actually didn't. They paid 0 British pounds. So one of the things we can do is change all of this to British pounds. So if I go up here and select the pound symbol, it will shorten that to 2 decimal places, because that's typical for money, and it will give me the pound symbol to keep me on track. But also notice it removes the 0, which I'm not terribly fond of. I like the 0 there, but nonetheless the dash tells me the same. Maximum, we can do that the same, obviously using the max instead of the min, J2 to J888, and calculate that. 512.33, you see it's the same. We can do the sum with the sum function. These are all, again, very straightforward. And so there we have the same value that's being calculated in the analysis Toolpak with the descriptive statistics. Now for range, there's not a range function, so I can simply do something like the maximum minus the minimum. Now, I already have these calculated, and so I could point at those cells, which I would normally do. Why? Okay, I would normally do that, and the reason I would normally do that is because the less you type, the less likely you are to make mistakes. Or put the other way, the more you type something that's already been typed in, the more likely you are to make a typing mistake. So I've already typed in the formula for max and the formula for min. So normally I would simply point at those cells. In this case, I want to show you how I'm doing this. And so I would do it this way. But normally I would simply say equals that cell minus that cell, and I would come up with the same value. That way, if I had made a mistake or I wanted to change something down here, it would be reflected in this. Now, this is interesting for many reasons. Number one, it's in pounds, and that's a little bit difficult for me to identify with. It's also in pounds from 1911, so that's even harder to identify with. And in a previous video, I showed going out to a website and kind of getting the conversion factor for that. And the conversion factor into 2019 dollars, which was the last available information from that website, was $131. So 1 pound in 1911 excuse me, equals $131 in 2019. And I don't have to quibble over whether that's perfectly accurate. There's different ways of calculating that. And so you will see ranges for these types of things. But this gives us an idea of what was going on. So what I'm going to do is create a formula. I'll just create it here. Equals, and that's in 05, but because I know I'm going to copy this down, I'm going to ensure that it's an absolute reference to the row times N14 to find out my range. And again, that's dollars, so I want to make sure I'm showing that. But wow, that's a large range. A little bit shocked at that. We can just drag this down and notice that the pound symbol here, that simply means that my column is not wide enough, and I can manually drag it, or I could just go up here on the column when I get this transition to this different symbol, and I can double click and it will auto adjust that to the width that I want. I like a little space between the number and the dollar sign, so I'll make it a little wider. Wow, they brought in 3.7 million in today's dollars. Someone paid $67,000 for a ticket, and someone paid nothing for a ticket. Now, I assume their experience was quite a bit different from one another as far as what they had access to. This leads me to the question, well, how many people paid nothing, and how many people paid $67,000? So this is where I can use my count if. So count if, oops, tab here, J2 to J8 is, oh, actually I'm doing this wrong. I want to count if the value is equal to 0. Oh, actually, there you go. Thought I was doing it wrong. I'm not doing it wrong because I'm now going to point at this cell that shows the value that I want to check for. And I'm going to make this an absolute reference. Actually, I'm not going to make it an absolute reference. And let me show you what Excel often does. So there were 15 people that paid nothing for their fare. That's interesting. I wonder why that is. I wonder where they had to sleep. Now, if I copy this down to find out how many people paid the maximum, there were 3 that paid the maximum, but notice this little symbol here, kind of a green triangle in the upper corner. That's because Excel notices that these two formulas are different, and they're different because when I copied this one down, it moved that range that I was selecting from because I did not use absolute reference to the rows. So indeed, when we look at this formula, it starts at J3 and goes to J889, which is not what I want. So this is a good reminder that, well, we can make mistakes, and sometimes Excel is kind to us and points. So pay attention to when it points. Sometimes you want the formula to be different. In this case, I don't. So rather than modifying this one, I have a habit of going back to the original formula and modifying it the way it should be. Excuse me. And that's a good habit to get into. And then I can copy this down. So notice the answer doesn't change. It could have. It's possible that the very first row would have been someone who paid this amount, but wasn't. So we have 15 people paying nothing and 3 people paying equivalent of $67,000. Wow. Now, this leads me to another question. I wonder how many out of our sample data set, how many survived? So we can use a count if s equals count if s. And let's see, we still want to know, one criteria is, of course, they paid this amount. But the other criteria is the survived, and that's actually in the A column. And I want to know if that's 1, because that's the dummy variable. 1 is set to indicate that they've survived. Ooh, that's not very good. What's the percentage of that? So let's do equals Q15 divided by P15 and set that to a percent. We'll just round off to a whole percent, 7%. Okay. Now I can copy this down, but again I have to set some things to absolute values here, or absolute references. And so it's always that criteria range that I want to set to the absolute reference, because I do want my reference to the amount, the reference to M15, I want it to go down to M16. And so we'll simply change that one and then drag it down. And oh, I don't even have to calculate that, but we'll do this. So 100%. Wow, that's telling about maybe where they were or what privileges they had. Interesting information we can learn from these descriptive statistics. Two other measures of variability are the standard deviation and the sample variance. And the standard deviation, it's worth taking a look at that formula. And so, as I've done before in this video, I'm going out to the web and doing a search for this. And so the very first thing I want to show you is the standard deviation for a sample. And we'll walk through this quite briefly. Essentially, the standard deviation is the average distance squared of each value from the mean. So if you had a line of people, right, and you designated one person as the center, this would represent our mean, and then you measure the distance of how far people are standing from that person, and you squared that. Notice this is the distance, right, or not the distance here. The distance is the value minus the mean, right, squared. We get that squared. Now, the reason we're squaring it here is because that emphasizes those larger differences. Okay, so we kind of want to know we're more concerned about larger differences than we are about smaller differences. So the design of this formula emphasizes those through that squaring. So we're taking the sum of all of those, and then we're dividing it by n minus 1, so our count minus 1, and we'll talk about that more in a moment, but taking the square root, and that gives us the standard deviation. Now, the standard deviation is in the units that you're using for your measurements. So in this case, it would also be in British pounds, so 49.78 British pounds, and we could certainly convert that to dollars. So if we just copy down one of our formulas that we had used before, and oops, I've done something wrong here, and so let's see what I've done. Oh yes, so I haven't calculated my standard deviation using a formula. So let's use a formula here. Equals standard deviation, and there's a P for population or an S for the sample. Now, we're using the sample, and I'm going to talk here in a moment about the difference, but we're using the sample, and that's what Excel is using in the analysis Toolpak, because we're finding out the standard deviation in this sample. So we're going to select the sample, and that is a J2 to J8. And I'm going to have that display in British pounds again. Show you that we calculated the same thing as the analysis Toolpak. And now we have our answer in US dollars 2019. And that is around 6,500 standard deviation. So it's kind of an average distance, but it's that average distance squared, so it emphasizes those that are further away, but it gives us an idea of how spread out these things are. Now, what's the difference between the standard deviation for the sample versus the standard deviation for the population? I'm glad you asked. Well, if we go back to that formula and we look at it, the bottom of the standard deviation for the population is n-1. Now I should point out that the standard deviation for the population is represented with an S. Whenever we're talking about descriptive statistics for the sample, we're going to use Roman letters, so our alphabet. When we're talking about descriptive statistics for the population, we're going to be using Greek letters. Okay, so we know this is the standard deviation for the sample because it's using a Roman letter, our normal alphabet. And the difference is that here it says n-1. Now if I go over to the page where I searched for the population standard deviation formula, and in part I'm searching for these to show you that you can find them, but also it's faster for me than typing all of this in Excel's equation editor. You can certainly enter these equations in Excel, in all of the Office suite using the equation editor. It just takes a little bit of time. So notice that this formula is the same. There's a sigma, which is a Greek letter, telling us that it's the standard deviation for the population. And notice that we're using the actual count, not the count -1, for the population standard deviation. Now, why would we do that? Well, because what we're doing is we're taking what's called a conservative approach to this number. The standard deviation, the higher the standard deviation, it means that there's more variance, variability in our data set. And so we want to be conservative on this and acknowledge that the variability of the actual population may be more than what we're calculating here. So the mathematical way of doing that is to, instead of dividing by 887 down here, which is the count, we divide by 887 minus 1. So 886 gives us a slightly larger number. And that's important to know when you're using Excel, and important to know when you're working with samples versus population and that type of a thing. Let's take a look at what the difference is. So if we say the sample standard deviation versus the population standard deviation equals standard deviation sample. That's the number we came up with before, and note both of these are in British pounds, so we'll go ahead and designate that here. And let's take a look at the standard deviation of the population if we assumed this was the population. Now it's not, we know it's not. It's only 887 out of the possible, say, roughly 2,500 passengers that there were. So, but this is to illustrate what that mathematical change does in change to. It lowers it a little bit. Not much. It lowered it by 3, well, I don't know what you would call that in British pounds, 0.03. Maybe it's cents. I don't know what they called their division at that level for the British pound, but it didn't lower it much, but it does lower it some. The larger the sample, the closer the standard deviation for the sample will be to the standard deviation for the population. And most often we're working with a sample because we don't have access to the entire population. It would be interesting to get the entire population for the passengers of the Titanic, and you could do these calculations on that to see what numbers you come up with. Nonetheless, there you have it, standard deviation and sample variance. I should comment about the units for the sample variance. Actually, I should explain that. I guess I haven't. I was getting a little bit ahead of myself here. Sample variance is the inside of that formula for standard deviation. So if we go back to, let's go back to this formula right here because we're talking about the sample. If we take away the square root sign, what's inside here is called your variance. And so technically what you do is you calculate the variance and take the square root of that to get your standard deviation. Well, so here is that number, and it's not, the units are not our pounds. It's actually our, whatever unit we're using, squared. Because of the aspect in this formula, because we're squaring this here, and we haven't yet taken a square root. So this is actually British pounds squared. Oops. Could put the 2 there, but we'll just write it as squared. That's actually the units that the sample variance or the variance is in, and in this case it's a sample variance. So you could certainly calculate that. There is not a Excel function to calculate the variance. Okay. The next set of descriptive statistics that we'll look at are measures of central tendency. So I've highlighted those here. We have the mean, the median, and the mode. And these are pretty straightforward. The mean is the arithmetic mean, and you can use the average in Excel, average, to do this. And again, we're looking at J2 to J888. And there we go. And again, these are all British pounds. So I'm going to change this so that we know what we're working with here. The median, that's the midpoint, so half above, half below. So we actually have a median function in Excel that we can calculate that with. And so there you go. We're coming up with things. Now, the mode, that's the value that occurs most often. And here it gets a little more complicated because there's a mode single and a mode multiple. And what the data analysis Toolpak uses is the single. So equals mode dot single. And again, that range. And I'm going to illustrate what the difference is here, but notice we have the same values there. So let's take a look at what the difference is. So if we look at a set of data, so let's just say we have a small set of data, 1, 2, 3, we have a couple of 3s, we've got a 4 and a couple of 5s. Okay, so if we do the mode single, I'll do it in this area right here, equals mode dot single, it's going to pick the mode dot single. Sometimes I miss my tab key. It's going to pick, oops, this is M23 to M29. It's going to pick the value that occurs the most often, but it's going to pick the first value that occurs most often. So it's giving us 3. If we were to reverse this order, right? So, well, let's just do it in a different location down here. 5, 5, 4, 3, 3, 2, 1. And we were to use the same function, equals mode dot single. And this is M31 to M37. Notice that it selects 5 as the most frequently occurring value, and that's because when you're using that mode dot single, the order matters. Okay, so you have to keep that in mind. Now there's also a mode dot multi for multiple, and so let me just do this here, equals mode dot multiple. Oops, again I missed my tab key, and that was M23 to M29. And notice there that the result is actually a set, and that set spills over into other cells. In fact, if we click off of this and then just for the sake of illustration come back on, you can see that this is the formula that I used up here, and down here there's a little blue box around the 5 saying that's connected. And in fact, if I click on that, the formula is there, but it's grayed out, meaning that all of those values come from that single formula and they've overflowed into multiple cells. So this is the best way of figuring out if you have multiple modes, meaning values, multiple values that occur most frequently, right? And the order doesn't matter here. If I do it up here, they'll be listed in a different order. Oops, mode first, not multiple. And 31 to 37. And they're listed in the reverse order, but they're still both there. So in many ways, that one's a better one to use. So we could come back up here and change our mode.single to multiple. Now, it's a little risky doing this here. Multiple. Hit the tab to finish that out, because if there are many that occur the same number of times, they'll kind of overwrite some of that data that I have there. So let's just save that. And oh, it's the same value. So there is actually one value that occurs the most often. So let's see what those are in US dollars, kind of following out what we had done down below here. So I'm simply going to take that formula that I have down here and copy it up. And interesting, so the most often occurring ticket price, just over $1,000 in today's, and the median, so the midpoint, right, half of the count or frequency is below this nearly $1,900 and half is above. And then the mean, or the arithmetic mean, what we often call the average, is right at $4,000, just over $4,000. Very interesting. Now, I wonder how many people, kind of what we down here, how many people paid the median and how many people paid the mode, right? So I'm going to copy actually all of these over to find out how many survived and what that percentage is. And okay, so 7 paid the median price, actually paid that amount. Could have come up with less or more, but 1 survived, so a 14%, a little bit better than those people who, actually twice as good as those people who paid 0, but certainly not the same as those who paid $67,000. Okay, and then for the mode, the most frequently occurring one, occurred 43 times out of the, what do we have, 887 down here as far as our count goes. And 5 of those survived, so 12%, still not real good. I don't know what the total survival rate was on there, on the Titanic. But thinking about total survival rate leads to a discussion about the difference between a sample and the actual population. So what we have here is 887 of the passengers from the Titanic. And I believe there were somewhere between 2,000 and 3,000 people on the Titanic. If you include the crew, it'd be up toward the 2,000 or 3,000. And if you don't include the crew, it would be down toward the 2,000 range. That's my understanding. And so we have a sample here. And the descriptive statistics that we are performing here are against that sample, right? So in our sample, we can say the mean is 32.31 British pounds, 1911 British pounds, and the median is 14.45, and the mode is 8.05 of our sample. And the idea is that a sample is representative of the population. But of course, let's say there are 2,500 passengers. You could take nearly 900 passengers in almost any combination, right? And so the mean, the median, and the mode that you get from those samples, there could be some variation in there. And that's where this idea of a standard error comes in. This is actually the standard error of the sample mean. And so it too is British pounds, right? So I'm going to change that to British pounds. And what that means is it's a calculation that tells us that based on the fact that we're taking a sample and based on the size of our sample, there's an error rate on our mean. So our mean probably in the actual population or any given sample from that population actually, would vary by 1.67 pounds. Now, there's not a formula function in Excel to calculate the standard error, but you can certainly do it on your own. And it's going to use something that's called the standard deviation, which we'll cover later, that's down here. But we can certainly plug that in, equals standard deviation, which is right here. I'm going to select the standard deviation of the sample, and which is what they use in what Excel uses in the analysis Toolpak. So, and that is my range. And that's going to be divided by the square root, so square root of the count of my range. So we know that to be the 887. So we're squaring that. So that's how we find it out. So we're starting with the standard deviation, which we'll talk about later. And we're coming up with an error. So we think our mean is within 1.67 British pounds of any mean that you would, any sample mean that you would pull from this population. Okay. Okay, measures of shape. We're going to talk about kurtosis and skewness, and I'm actually going to start with skewness on this one. So the idea of skewness is that the sample itself is, well, a zero skew would be a sample that's symmetric. So we could, as it were, chop it down the center where the mean is, and the two sides would be mirror images of one another. So you might think about the normal distribution as having a skewness of 0. Well, it actually does. And in fact, if we were to go out and just search for this, just a Google image, I've already done it, normal distribution, just to give you the visual of this, because we are talking about measures of shape, and it is very helpful to see those in a visual form, because that's what we're talking about, is the shape. So somewhat at random, selecting an image. I like this one here. This is what we're talking about with the normal distribution, and we'll get into more later in a different video demonstration. But for right now, we can see that the mean of this population right here is right down the center. And if we chop it in half there, we can fold it over there. They're identical. That would be a skewness of 0. Well, I've done the same search, but this time for skewness. And again, picking one of these that is helpful. We can see this. Here's the normal distribution, and there's our mean, right? So if you divide it in half, it flips over on itself. It's a mirror image. But if we have a positive skewness, that means the right-hand tail is longer. And you can see this, that with our mean right here, we can't fold it over, right? We have it's positively skewed. And that's going to be a higher number on the skewness range. And then if it's negatively skewed, as in this image right here, again, we can't divide it or cut it by the mean and fold it over. They're not identical. A negative skewness is the left-hand tail is longer. So I think the visuals on those are very helpful. Now, notice here that we have a positive skew of 4.77 in the data set that we're looking at for these British pounds. And one thing to keep in mind is both kurtosis and skewness, the numbers are simply just numbers. They're, if you will, a relative number compared to all of the possible skewness or kurtosis that you could get, and typically compared to a normal distribution. So with skewness, normal distribution is 0, so we have a positive skew, meaning that the right-hand tail is longer. Now, we can do that ourselves with the skew function, very well named for us, but notice that when I select this, there is a skew and then a skew.p. The .p would be for the population. We're doing the sample, and unfortunately, they don't follow the same naming convention for this, because if it did, it would be skew.s for sample, nonetheless, it is simply skew J2, oops, and we get the same answer that we have here for skewness that the analysis Toolpak gave us. So that's great. So let's talk about kurtosis. And kurtosis is the idea of the flatness or the peak of a distribution. And again, it's helpful to go out and search for these. So I've done that and brought up various images here. I'll select this one. And you can see here that we have a normal distribution in the center here, right? Kind of a mid-height distribution. Now notice that all of these are shown with no skew. The mean is the same for all of these, and the skew is 0. Again, meaning that you can divide them by the mean, and you have mirror images on either side. You can fold those over. But we have different kurtosis. So we have one that is more flat here, meaning that the flatter it is, the tails, we have more in the tails in comparison to that center, right? And then we have one that has more of a peak here, and this would be a negative, I'm sorry, the flatter one is a positive kurtosis. The negative one, or the peaked one, is a negative kurtosis. And again, the mirror image, no skew, but most of the readings are very close to that mean. And by that, I mean, remember that we're talking about counts here, or frequency. So how many of the readings fall within this, whatever the scale is that we're using for that. So as I pointed out before, kurtosis and skewness is just a number. Now, the kurtosis of the normal distribution is 3.0, but oftentimes what we're given is an excess kurtosis, and that's what Excel gives us when it calculates this, is an excess kurtosis. So it actually subtracts 3 from it. So for practical purposes, when you're looking at Excel, you can think about the kurtosis of a normal distribution being 0 compared with the number that you have in front of you. And in fact, we can do this calculation, KURT, short for kurtosis, and put in our range. And here we go. We have the same number. So that is what the analysis Toolpak is doing for us. So both of those are measures of shape, and they give us an idea of how it compares to that normal distribution. Now that we've gone through all of these descriptive statistics, it's time to take a look at a visualization of this and begin to put some of these things together from the standpoint of, well, what does it look like? So we've done all of these calculations right here using the feature in the analysis Toolpak, and then we've also repeated those and taken a look at, well, how would we calculate those individually if we wanted to do that, which oftentimes we want to do that, right? So, well, what does this look like given the fact that we have this skewness of 4.77 and the kurtosis and our standard deviation and the mean and that type of a thing? So I'm simply going to select my column F to select my data, and then come up here and do an insert, and typically we can do recommended charts, and in fact Excel gives us one that works quite well, and this is the bar chart with this Pareto line on here. Now what the line tells us is, well, of all of the count, right, the 887 that we're looking at, what percentage are included as we move this direction in our particular chart. Now, first of all, notice that this is nowhere near what a normal distribution would look like. We have our peak here at the 0 to 18 pound range. And in fact, we get out, wow, our percentage is just nearly 100% by the time we get out here, but we have values that this long right hand wing is, we've got lots of values out there. And so this gets to our kurtosis and our skewness, so that right-hand tail, I called it a wing, sorry, the right-hand tail is, we're very positively skewed in this case, and we see that we have a value of 4.77. Also, that idea of kurtosis, the idea that, well, this is excess kurtosis, so it's positive and it's much flatter than a normal distribution would be, and that's again because of this very long tail that we have here on the right-hand side. There is no tail on the left-hand side. So visually, it helps to look at these, to run these descriptive statistics using the analysis Toolpak, but also look at the visualization of it to kind of get a feel for, well, what does a certain kurtosis look like? What does a certain skewness look like? And that type of a thing. So there's other visualizations that we could do, but we'll save those for later.